Two is exercise 7. It starts in the workbench where you end up having to extract both near and far amplitudes. You can ignore the section about moving your amplitudes back to the PC. Those have already been copied back and put there for you in order to expedite things. There was a lot of button pushing without much intellectual content. Was the strong input from the first time we gave the course. And but before you sort of get into that, I wanted to go and quickly sort of show you the AVO analysis spreadsheet and get you sort of familiar with it. It's similar to the amplitude analysis, but fortunately or unfortunately has a few more bells and whistles in it. Okay, down in the center.
I have 3 minutes left on the tape. You want me to change it?
No, I'll be through this hopefully. Okay. Now, here you go, and you'll see that right here it looks very familiar. Differences are that you have near and far amplitudes and areas coming in is the major sort of difference in it. You see right away you have sort of familiar load wells buttons. You can background map normalize. I made it so that it automatically bypasses, though. You have to sort of explicitly want to do that if you want to. It shows all these maps. Here's the far area, far amplitude, near area, near amplitude. Well, the background map I'm not using. There's a depth map. There's also a width map here, similar to before. Just as before, you go in, but now it asks you to pick both brine and hydrocarbon clusters from the raw data. You go and you do that as before. Pick the potential brine lake first here, just as before. And it will wait forever for you to do this, as some of you found out before. And now it shows you where those extracted clusters were, and they probably look familiar from that view graph. You see they're in these millivolt odd units here. It also will tell you to the right what the mean and standard deviations and orientations of those ellipses are. The next thing is that it will go and need to go and figure out how to normalize this. And there's a lot of games that you're going to play, and really, quite frankly, the art and the expertise lies in really figuring out what these numbers should be. These should look familiar to you. These are the ones that ended up coming from the wavelet derivation. The next thing is, once you decide on this, it will actually normalize stuff and apply that transformation for you. And also go and add those maps together for you to give you sort of normalized maps. Goes and will calculate, once you've figured out what these optimum lithology and fluid directions were from your modeling and have input, whether or not those are fars or nears and the like, you can go and click and now go and get the things that go both along the lithology direction as perpendicular to it. And you then can go, in terms of the fluid coordinate, ask what is the value of that fluid coordinate in your sort of target area. And it'll actually even tell you what the lithology sort of average values are. And you also can do stuff around the arbitrary path. And then it does the Bayesian update, but now in terms of these calculated both near and fars. And so now you'll see these probability maps come up. And you see that one of these have been zeroed out. I just did that by sort of zeroing the prior probabilities. you go over here to where the clusters are, this is where I specified the theoretical clusters that came from the rock physics spreadsheet, and also specified what the theoretical lithology direction and fluid directions are. You see that the fluid direction is a far stack and the lithology direction is a gradient stack. And that again was calculated with, through the rock physics spreadsheet. And you can again go and integrate to find the volumes. And so here is the area above the fluid contact. Oh, I didn't calculate the net sand first, sorry. And so if I want to integrate again to find the volumes, I'll just go around, integrate, and you'll actually have a little histogram so I can see that I have about, on average, about 30 meters of net sand there. And it also comes up with the same volumetric estimates. And I can also go and translate these things into true XY coordinates as before and output them in the XY coordinate system by clicking this button. It's taking a little while to think, but now it's coming up with the answer. And all of the important maps are translated and plotted for you here. Okay. So I think that you probably get the feeling that this workflow is very similar to what we did before. The things that are different is that instead of just dividing the amplitude map by a number, we have a 2x2 matrix transformation, and that we also end up having the concept of the sort of fluid horizons and lithology, because now there are really two optimum directions that we want to take a look at. Okay? And so what you end up doing is go through, take a look at this. And another thing, when you go and take a look at the amplitude extractions, think a little bit about picking it. You're going to realize how hard it was to pick this because it was polarity flipping. Okay? And so from the interpreters here, I mean, it's not easy. And think about what your picking strategy would be for a polarity flipper such as this. And then after you take a look at the amplitude extractions and the way that works, you'll see that you snap to a different level for the near versus the far, for instance. And then after you've thought about this, then get in and sort of go through what the normalization is. And I walk you through a couple of different ways of deciding what the normalization is. And that probably will take you a bit of a while, and I probably would recommend going through it while you're sort of fresh mentally in the morning in terms of trying to understand how we normalize this stuff. Okay? So anyways, I'll let you go. The QI workbench session, just choose the Star Lifter project and exercise 7 as your session. And hopefully we'll be able to be walking through this together. You're going to have to go and make these sort of same decisions when it comes to the lease sale. And fortunately or unfortunately, your particular bids will, in a way, will be significantly influenced on what your particular choice of normalization will be.
Okay.
And it's one thing that we found. So that's the reason why that I'm going and sort of focusing on it, and also the way that we end up tending to try to understand what the background normal is, or the shales, or really what we're going to go and use as a baseline in order to find anomalies, ends up being, I think, the most important thing, but also one of the things that I sort of talk about it as sort of the heart surgeon type thing, that you end up having a lot of parts of heart surgery in terms of opening up the chest cavity, closing the chest cavity, that are fairly straightforward things that you can teach fairly easily, and people can pick up and do proficiently very early. When it comes to going and determining how to normalize these amplitudes, where and how to normalize them, it's a lot more like the particular, attending heart surgeon, where it's something that you have to be around for a while, you have to build up an experiential base, And it's one thing that takes quite a bit of judgment in terms of what you do, but it's also something that's very critical in terms of the decision-making process eventually, because that ends up sort of adding in, or if you make a mistake, it's a systematic error that you'll have in terms of your amount of pay. Amount of pay is value, and value is what you can bid or not bid on something, okay? And so the particular part I'm going to focus on is this thing where it says pick the unnormalized clusters. Then we're going to look at these numbers and then choose what these normalization coefficients are for these wavelets and the like here. And then go on down to the next step, okay? But I'm going to be going and doing, sort of showing you this normalization quite a few times, and this is really practically, I think, how you end up doing it. Now, the first thing that I'm going to go and do is go ahead and pick my clusters. I told you to first of all pick an area that you end up thinking is the down dip brine, and then the up dip hydrocarbon. Okay, and really, I think that you'll find that you'll get these clusters no matter what the detail really is of the with respect to that polygon that you end up picking. And again, this is something that should be fairly familiar from the view graph that we had yesterday. Let me go and I'll get the.
So you don't have to have a high level of fidelity when you carve out those polygons. You
No.
kind of just.
Yeah, go and try it yourself. You know that. You know, if you just sort of cavalier grab the up dip and grab the down dip, you're going to get something that looks about the same. I'm actually sort of surprised because I do it a lot, you know, in this course, and you know, it's fairly easy for me to get something repeatable. I don't have to be really careful about where I do grab it. But if you go and decide that you're going to focus on some small little area here, that obviously will make a difference. So if you go, but if it's one of the broader areas, it normally, at least for this exercise in general, you tend to get these particular polygons. Now, the one thing, and the first thing that I told, I sort of talked about a bit, but I didn't really go into, was looking at what these particular clusters are and what the sort of the expectation is for gas, oil, low saturation gas, brine, and shale. And the two things we're looking at here are going to be brine, and I'll take a look at the mean reflection coefficient for brine should be about 4% positive, decreasing to about 2%. And gas, which starts just about transparent and then increases up to about -4%. The first thing to note that these are modest reflection coefficients. They're not the 20% shallow gas reflection coefficients that you would get otherwise. We are choosing and we are normalizing here on the gas and the brine. You could also even choose to do that on the shale if you wanted to. And in fact, that is another particular option to make sure that the shale is coming into the right location. But the one thing I want to talk about a bit is that what happens when your mean expectation is 0, okay? And what you normally try to do is find out a particular constant that's going to go and transform from millivolts into the reflection coefficient units. But that ends up having this particular number in the denominator, okay? In other words, small changes in this number can make very large changes in what that particular conversion factor is. And when I talked about saying that the hydrocarbon sort of for the near reflection coefficient really has very poor sensitivity, you can identify that by the fact that you end up getting a very small reflection coefficient. And dividing by 0 ends up giving you a very poor sensitivity. And so when I go back here to the workflow, there are two different ways that I can go and determine what these particular coefficients are. And those are going to be the CN and the CFs. okay? One is by making sure that the brine is in the correct location in the two-dimensional space, or to go and assume that the hydrocarbon is in the right place in the two-dimensional space. Well, that is assuming that I know the B value, and the B value theoretically should be 1, so I'm just going to put it at the most likely or the theoretically correct value. Now, if you take a look at B, does not influence your choice of Cn, mostly because you end up having a very small angle normally on the near, and so this coefficient is 0, and so Cn ends up just getting, multiplied by the near reflection coefficient in order to give you the amplitude. And so you can go and estimate Cn sort of independently of B, but you go and you see there are two numbers that are quite a bit different here. Well, this huge number came from the fact that small differences in that denominator can make huge differences in the reflect or this normalization coefficient. And so I'm just going to explicitly delete it, and it's really a statement that this is something that we really shouldn't be looking at. And the best estimate here of the Cn ends up being 13,000. If it was not the case and both of these ended up being good estimates, they should then be about the same number, and you would go and sort of take an average of the two in order to be able to put into what the particular Cn value should be, okay? Okay, now though, we end up having a bit of a conundrum because we know we have good sensitivity for the CF for both the brine and hydrocarbon. Both of them have fairly good reflection coefficients. One's minus 30,000, the other one's plus 40,000. They're not even the same sign. And so I'll go scratch my head. Well, I'll throw up a coin. I'll pick one of these numbers to show you. I'll try the minus 31,000 here. And this is what I've sort of told you to do sort of in part A. And I'll put in the minus 31,000. And I'll go take a look at these clusters and sort of see sort of how they come out if I go and force things in that fashion. Well, you actually have kind of a problem here. That you go on, and I said because I chose the brine one, the middle of the brine cloud, or the down dip cloud, now sits in the middle of the brine response, okay? Because we told it to. But, I mean, the hydrocarbon, I don't know, it's going out here into hyperspace, okay? It makes no sense. Also, if you take a look at even the brine cloud, even though it's sitting at the right point, it has the wrong orientation. It should be pointing in this direction, and it's out by about 45 degrees. Well, okay, I had two choices, okay? Let me go and pick the other choice, which is the minus 40,000, okay? Positive 40,000, I'm sorry, yeah, positive 40,000. Let me go and take a look at that. Well, okay, I mean, we're a little bit better, okay? But you can actually go now and see that, really now the brine is actually now has the wrong orientation. It gets further away. The particular hydrocarbon, is having trouble, even in this case, coming in to the correct location. And so, overall, again, that you have the wrong orientation. Really, nothing ends up sort of lining up, okay? And so, well, okay, and at this point you say, well, there maybe is a bit of rotation, and so let me take B and increase that up to 2. Wow, okay, well, this is a big number compared to that, but at least they're of the same size. Well, so now let me just go up to 3. Wow, okay, there we're getting closer. We're at 23,000. And then let me go down, let's say, to maybe 3.5, or up to 3.5. But now I'm at about 16 and 13,000. So, okay, let me just have a number that's about halfway, in between these two, which would be, let's say, about 14,500. Okay. And now let me go and take a look at the way that the particular clusters come out. Oh, I'm sorry, I went through them. I'm sorry, let's see if we do it again. Okay, now you end up seeing something that's much more pleasant in that the orientation of the cluster is correct. It's a little bit too narrow, but then the particular, though, hydrocarbon has now actually going from brine to hydrocarbon is now also oriented in the right direction and has sort of moved down from the brine and sort of changed orientation properly. It is, though still a bit bright, okay? And in an exploration sense, this is probably where we would stop, okay, and say that we have gone and have normalized the down dip to be correct and would be, fairly satisfied at this point. Another thing that you could do to also sort of double check at this point is to go and say, okay, I'm going to go and sort of pick a particular cluster where, let's say, I think that we could have been shale. Let's say it's someplace like right here. And I'll just pick another place where I, think things could have been shale, which is sort of down in this area. And now you'll see those both overlie each other. And then if I go and say normalize these things, according to that normalization, that what you would like to see is that these particular clusters end up being relatively consistent with the particular black model cluster, which is what your particular prediction for shale is, okay? And so, at first I went and asked, okay, I'm going to go and determine things, trying to make sure that the brine has the right ADO response. And also, it should simultaneously give the fact that the hydrocarbon also has the right ADO response. And you also can take a look at whether or not it would be consistent with the shale, okay? And so there are three ways that you could go and choose to normalize this ABO response, and that you really do need to make sure that sort of everything in the end looks proper. And that now that we've done this for one prospect, that if you were going and had multiple levels or multiple prospects around the area on the same seismic survey, one thing I really want to accentuate is these numbers should remain constant so that you're not changing the normalization as you move around, unless you significantly change the depth that you're at and you really think there is a significant change in what the compaction state is, or in terms of what the rocks themselves would look like. And so anyways, I wanted to go through some of this logic. I'm going to go and give you a little bit more time so you can work through it. And then after you've done this, though, the rest of this stuff ends up being a fairly straightforward sort of click and go forward. But the one thing I did want to go and talk to you, though, a little bit more about were the particular lithology and overall fluid coordinates. Because once we go and decide to normalize, well, let me say one other thing before I move on, is that if you will go and check what these numbers were as came out of the wavelet derivation, if you remember, B was 2, one was about 19,000, and the other, can some people just sort of tell me quickly? I remember B was 2, right? What was CN? 19?
13, I think you're right.
Okay, what was, when CF was? 16,000, okay? Okay, and before I go there, you can see that if you use the derived numbers, that, well, I'm sorry, I need to go and repick the original ones.
You did the shit.
Yeah.
Or Brian's. Yeah, he said shit.
Brian said. So then now if I normalize the clusters, yeah, you do see that it does look better. This one starts being about the right width. They are normalized in sort of the right direction. The brine, and this had been very hard to understand beforehand, ended up being snuggled sort of in this 1/3 of the overall cluster that you ended up having in terms of what was observed here. I think that you do realize it is better, but we at least got to within probably 30 to 40% of the correct numbers in terms of these two numbers and this number. And that in an exploration setting, that's normally about as good as you can expect. Now let me go and we'll go and we normalize the clusters and plotted these amplitudes. And now let's sort of calculate the lithology and the fluid coordinates. And I was asked to go and say what was the particular sort of up-dip result, and showed me for both lithology, and it also had it for the fluid in terms of what that is. Let me sort of go and take a look here and talk about this though just a little bit. That there are two particular coordinates that come out here. One of these, if you take a look at it, and let's take a look at it again to remind you from yesterday, the lithology is the gradient stack, and that the fluid is best discriminated by looking at the bar stack in this case. And so if I take a look at the model clusters and what the value is for the lithology and the fluid direction, you end up seeing that there is a very big difference if I'm looking at fluid, okay, in this case, between the gas and the brine response. I'd actually set the low saturation gas and oil to the same values here. But if I go and take a look at the lithology direction, there's less of a difference between the gas and the brine, but there's more of a difference, but there still is a difference between the brine and the shale, okay? And so you go and reduce the contrast between things where you have the fluid, but still maintain a fairly good solid contrast between the brine and shale. And so what does that look like on these graphs that I ended up having? That's the fluid area. Yeah. You take a look at the fluid coordinate, that ends up being a very crisp delineation between the up dip area and the down dip area, and sort of has the maximum contrast, but it can be kind of hard to follow the way that the sand is going in the area below the contact. So now if I go and take a look at, let's see, I think it's 25. If you take a look at the lithology, that you end up bringing out a lot more of this sort of channelized belt behavior, and you see almost very little contrast as you go across the particular fluid interface here, okay? And so that what we end up doing in this case is use this lithology map in order to go and decide sort of how much sand that we have, and end up using the fluid to define where the particular fluid contact is, okay? So anyways, I'll let you guys go and give you about another about 10 minutes to sort of play around a bit yourself with the spreadsheets, and then we'll start the the last major lecture. Okay.